Welcome to this lecture on proportional and optimum allocations. Imagine you are organizing a massive food tasting event to understand the preferences of an entire city, but you have a strict budget and can only invite exactly 100 people. How do you choose them? If you pick completely at random, you might miss smaller neighborhoods entirely. This is why statisticians use stratified random sampling, dividing the population into distinct groups. But the big question is exactly how many of your 100 invitations should go to each specific neighborhood? This critical decision process is called allocation. And today we will master the two most important methods to do it. Now that we understand the premise, let us look at the core problem. In stratified random sampling, we divide our entire population into non-overlapping, distinct groups, which we call strata. For example, an apartment complex, a suburb, and a rural outskirts. Once divided, we must take a small sample from each group. But how do we divide our limited total sample size among these groups? This is the problem of allocation. We will explore two main ways to make this choice. The first is proportional allocation, which distributes the sample based purely on the size of the group. The second is optimum allocation, which makes a smarter choice by also considering how diverse the group is and how much it costs to survey them. Let us start with the most straightforward approach. Proportional allocation is the simplest and most intuitive method for dividing up your total sample size. The rule is simple. The sample size drawn from a specific group must be directly proportional to the total population size of that group. If a neighborhood makes up exactly 30% of the city's population, it receives exactly 30% of the survey invitations. Bigger groups get more representation and smaller groups get less, keeping the ratios perfectly balanced. This guarantees that your final sample is a miniature, perfectly scaled down replica of the entire population. It is incredibly popular in real-world surveys because it requires no advanced knowledge about the groups other than a basic head count. This concept translates into a very elegant mathematical equation. The formula for proportional allocation tells us exactly how to calculate the sample size for any given group. Here, n sub h represents the number of people we need to sample from a specific group, known as stratum h. The symbol n stands for the total overall sample size we are allowed to collect. Capital N sub h represents the actual total number of people living in that specific group. And capital N is the grand total population of all groups combined. Looking at the math, if the population of a specific group increases, the fraction grows larger. This means we must allocate a larger sample size to that group, perfectly mirroring our intuitive understanding. While proportional allocation is easy, sometimes just looking at the sheer size of a group is not enough. This brings us to optimum allocation. This is a more advanced, highly strategic method that tries to get the most accurate estimate possible without overspending a fixed budget. Instead of just looking at size, it looks at three crucial factors: the size of the group, the amount of internal variation within the group, and the financial cost of surveying one single person in that group. Variation simply means how different the people in the group are from one another regarding the survey topic. If a group has highly diverse and conflicting opinions, or if it is incredibly cheap to survey them, the optimum strategy tells us to sample more people from that specific group. Before we can allocate our sample optimally, we must mathematically define our budget using this cost function. Here, capital C represents the total amount of money we are allowed to spend on the entire survey. The symbol C0 represents the fixed overhead costs. These are expenses we have to pay no matter what, like renting an office or buying software. The symbol C sub H represents the specific cost to survey just one single person in group H. This might vary significantly if some groups live far away and require expensive travel. Finally, we multiply this by the number of people we sample from that group and sum it up across all groups. If we increase the sample size for an expensive group, our total cost will shoot up very quickly. Using calculus to minimize error within our budget gives us this master formula for optimum allocation. The new symbol here is capital S sub h, which represents the standard deviation, or the amount of internal diversity within group H. Notice carefully where each variable sits in the fraction to understand how it works. The group size and the diversity are in the numerator. This means if a group is larger or more diverse, the formula tells us to increase their sample size. However, the cost is in the denominator. This means if a group becomes very expensive to survey, the fraction shrinks, and the formula forces us to sample fewer people from them to save money. It is a perfect mathematical balancing act. This formula we just saw leads us to an important special case called Neiman allocation, named after the statistician Jerzy Neiman. We use this simplified version when the cost to survey a person is exactly the same across every single group. Because the costs are identical everywhere, they mathematically cancel out of the previous equation entirely. Under Neiman allocation, we only care about two things: how big the group is and how diverse its opinions are. If two groups are the exact same size, but one group has wildly differing opinions while the other group all thinks exactly alike, Neiman allocation will smartly assign a much larger sample size to the diverse group to capture all those different viewpoints. Before we move on, let us see this with a concrete example. Imagine a school with two groups, undergraduates and graduates. We have enough budget to sample a total of 60 students, and the cost to survey everyone is equal. There are 1,000 undergraduates with a high standard deviation of 10. There are 2,000 graduates, but they are more consistent with a standard deviation of only 5. Our strategy is to use the Neiman allocation formula. First, we calculate the priority weight for the undergraduates by multiplying their population size by their diversity score. 1,000 times 10 gives us a value of 10,000. This represents how much priority this group should get based on its size and high variation. Continuing with our calculation, we next find the weight for the second group, the graduates. We multiply their larger population size of 2,000 by their smaller diversity score of 5. Interestingly, this also gives us a value of 10,000. Even though there are twice as many graduates, they are twice as consistent, so their overall priority weight ends up being exactly the same as the undergraduates. We now add the weights of all the groups together to find the total denominator for our formula. Adding the 10,000 from the undergraduates and the 10,000 from the graduates gives us a grand total of 20,000. This number represents the total combined priority of the entire school population. Now we calculate the final sample sizes. For the undergraduates, we take our total allowed sample of 60 students and multiply it by the fraction of their specific weight over the total weight. Since their weight is exactly half of the total, they get exactly half of the sample, which is 30 students. Finally, we do the same for the graduates. They also represent exactly half of the total priority weight, so they also receive a sample size of 30 students. Physically, this result tells us that even though the graduates outnumber the undergraduates 2 to 1, we should sample them equally because the undergraduates are so much more unpredictable and diverse that they require extra attention to measure accurately. Now, let us tackle a more complex, real-world scenario using the full cost-weighted optimum allocation formula. Imagine a health survey covering 2 regions. The city has 1,000 people, a standard deviation of 4, and costs only $1 to survey. The remote mountain village has 2,000 people, a standard deviation of 5, but costs $4 to survey. We can sample exactly 80 people in total. Because costs differ, we must divide the priority weight by the square root of the cost. For the city, we multiply 1,000 by 4 and divide by the square root of 1. This gives a final priority weight of 4,000. Because the cost is so low, their priority remains very high. Next, we calculate the cost-adjusted weight for the mountain village. We multiply their larger population of 2,000 by their standard deviation of 5, giving 10,000. However, we must divide this by the square root of their expensive $4 cost. The square root of 4 is 2. Dividing 10,000 by 2 gives us a final priority weight of 5,000. Notice how the high cost severely penalized them. If travel were free, their weight would have been a massive 10,000. We now add the cost-adjusted weights of both regions together. Adding 4,000 and 5,000 gives us a grand total weight of 9,000. We will use this total to find the exact fractions for our sample allocation. To find the final sample sizes, we multiply our total allowed sample of 80 by each region's fraction of the total weight. For the city, 80 times 4,000 over 9,000 gives 35.55. We round this to the nearest whole person, giving 36 people. For the mountain village, 80 times 5,000 over 9,000 gives 44.44, which we round down to 44 people. Practically, this shows the true power of optimum allocation. Even though the mountain village has twice the population and more diversity, the high cost of reaching them forces us to take a slightly smaller sample than we would have if travel were free, perfectly balancing accuracy with our strict budget. Let us look at a visual summary of the core difference between these two methods. On the screen, you see two groups. Stratum A on the left has a massive population but very low variance, meaning everyone is similar. Stratum B on the right has a tiny population but high variance, meaning opinions are scattered. Follow the arrows down. Under proportional allocation on the left, the method blindly follows population size, taking a huge sample from A and almost nothing from B. But look at optimum allocation on the right. It intelligently shifts resources toward the smaller group B, simply because its high internal diversity requires more investigation to understand properly. This diagram perfectly captures why optimum allocation is so powerful. Now that we have used these formulae, let us understand a fascinating mathematical relationship between them. It is highly illuminating to see how these two seemingly different allocation methods relate to one another. We know that optimum allocation is the smart method because it adjusts the sample size based on how diverse each group is. But what happens if every single group in the population has the exact same level of internal diversity? In real life, this means that the people in the apartment complex, the suburb, and the rural outskirts all have the exact same amount of variation in their opinions. Because there is no difference in diversity, there is no longer any strategic advantage to oversampling one group over another based on variation. Let us see what happens mathematically. Let us prove what happens under this condition. We are setting out to show how the complex formula simplifies. We start by defining our specific condition. The standard deviation for every single group is exactly equal to a single constant value, which we will just call capital S. Next, we take our standard Neiman allocation formula, which normally relies on different standard deviations for each group. We then substitute this constant S into the formula, replacing every individual S sub h. By doing this, we can see that the constant S now appears in every single term in both the top and the bottom of the fraction. This sets us up for a beautiful algebraic simplification in the next step. Continuing our derivation, because S is a constant number, we can factor it out of the summation in the denominator. Once it is factored out, the S on the top and the S on the bottom perfectly cancel each other out. After the standard deviation cancels out, look at what is left in the denominator. It is simply the sum of all the individual group populations. Mathematically, the sum of all group populations is exactly equal to the grand total population, capital N. Substituting N gives us our final result. The resulting formula is exactly the formula for proportional allocation. This proves a vital concept. If every group has the exact same amount of internal diversity, the advanced optimum method automatically defaults to the simple proportional method. So we have proven how the methods connect. This brings us to evaluating our accuracy. When we use a smart strategy like Neyman allocation, we expect our statistical error to be very low. We measure this error using variance. By substituting the Neyman formula back into the general variance equation, we get this beautiful closed form equation. Here, V opt stands for the optimum variance, which is the lowest possible error we can achieve. The symbol W sub H is the stratum weight, simply the fraction of the total population in that group. The first part of the formula shows the mean source of error shrinking as our total sample size n gets larger. The second part is a small mathematical correction factor for sampling from a finite population. This formula proves mathematically that Neyman allocation produces a smaller error than proportional allocation. We have covered a lot of ground today, so let us reinforce the most important ideas. First, proportional allocation is your baseline. It divides samples based purely on the size of the group, creating a perfect miniature of the population. Second, optimum allocation is your advanced tool. It ensures every dollar buys maximum accuracy by balancing group size, internal unpredictability, and financial cost. Third, Neyman allocation is simply the optimum strategy when your costs are identical everywhere. And finally, we proved that these are not entirely separate ideas. If all groups have the exact same variance, the optimum method elegantly collapses back into the proportional method. You now have the mathematical tools to conduct highly accurate real-world research. Excellent work today.